All right, let's open up a case file on one of the deepest, most stubborn mysteries in all of science. We're talking about a detective story where the crime scene is reality itself. The clues, well, they're woven into the very fabric of the universe. So let's start digging.
So here's the core puzzle, the central question that gets this whole investigation started. Why does it feel like the universe is playing by two completely different rule books? You've got one set of rules for the bizarre, tiny world of quantum particles, and a totally different one for the solid, predictable world that you and I live in. How can both of those possibly be true at the same time? I mean, think about it. Down in the quantum realm, a particle can literally be in many places all at once. That's called superposition. It's a world run by probability. But in our world, my coffee cup is right here, on the table. That's it. It's a world of certainty. The crazy thing is, the math behind quantum mechanics says this superposition idea should apply to everything, from atoms to coffee cups. So where does it go?
So here's our game plan for cracking this case. First, we're going to survey the scene of the crime, this tale of two realities. Then, we'll round up the usual suspects, the classic explanations for all this. After that, we follow a hot new lead called spontaneous collapse theory, see what the forensics team is doing to test it, and finally, we'll venture into the strange, uncharted territory called the Great Quantum Desert.
Okay, first things first. Let's get our facts straight and really lay out the scene of the crime. What is this conflict between these two realities all about?
At the very heart of this mystery is a principle called linear superposition. You see, the fundamental equation of quantum mechanics, the Schrödinger equation, is what we call linear. And what that means is if a particle is here is a possible reality and a particle is there is also a possible reality, then the particle is both here and there has to be a valid reality too.
And this quote just nails the problem, doesn't it? This rule, superposition, has been proven over and over again in countless experiments with electrons and other tiny things. But as we all know from just, living our lives, we never see a table in two places at once, or a chair, or a person. So what gives? What happens to this fundamental rule of the universe when things start getting bigger?
And that right there, that is the quantum measurement problem. The theory, the math, predicts one thing: universal superposition for everything. But our actual observation of the big macroscopic world shows something completely different. The second we try to measure or even just look at a quantum system, its whole cloud of possibilities seems to just collapse into one single definite reality. But why? What's making it collapse?
For decades now, physicists have been proposing solutions to this. So let's do what any good detective would do and round up the usual suspects.
So, suspect number one is the Copenhagen interpretation. This one comes from the founding fathers of quantum mechanics, and it basically throws its hands up and says, there's a divide. That's just how it is. Measurement causes a collapse. Don't ask why. Suspect number two is the many worlds interpretation. It takes a totally different path. It says the math is always right, collapse never actually happens. Instead, every single possible outcome just splits off and plays out in its own separate parallel universe.
But here's the big weakness with both of these classic explanations. They're more like philosophical interpretations than actual physical theories. They don't give us a physical reason, a mechanism, that we can actually go out and test in a lab. They're fascinating stories, for sure, but they don't give our investigation any concrete evidence to follow up on. Which finally brings us to a new lead, a suspect that isn't just a story, but a real physical theory that we can actually put to the test.
And this is such a cool idea. What if the Schrödinger equation, that bedrock of quantum theory, isn't the whole story? What if it's just an approximation of something deeper, a more fundamental law of nature? A single law that applies to everything, from the smallest electron to the biggest elephant, and explains why they act so differently.
So how would that even work? Well, this theory proposes that the Schrödinger equation is just missing one tiny extra piece. And this piece represents a universal random noise that's happening everywhere, all the time, throughout space-time. Now, for a single tiny particle, this noise is like one person whispering in a packed football stadium. You'd never even notice it. But for a big object, like a baseball, made of trillions upon trillions of particles, it's like all those trillions of particles are whispering together. The effect amplifies into a roar, and that roar forces the baseball to pick a spot and collapse into one single state. So you can think of it like this. There's this constant random jiggle happening everywhere in the universe. And it's not the act of us measuring something that causes the collapse. It's a continuous physical process. This background jiggle is always there,
constantly forcing big objects to pick a side, to collapse their wave function into a single definite place. The quantum world is small enough that it can ignore the jiggle, but our classical world can't.
And here's the best part, the most exciting part. If this universal noise is real, we should be able to detect it. Or maybe more accurately, we should be able to find the exact point where its effects get strong enough to break superposition. So let's head over to the forensics lab and see how they're hunting for the evidence.
You know, scientists have been pushing this boundary for nearly a century. We started with single electrons, way back when. Then in 1999, we managed to put these big buckyball molecules in two places at once. By 2011, we were doing it with molecules made of over 7,000 parts. Every single experiment just keeps confirming that quantum rules hold up for bigger and bigger things.
But, and this is the really mind-blowing part, the gap between the biggest thing we've ever put into superposition and the smallest macroscopic object we see in our daily lives is a factor of 10 to the power of 15.
Yeah, that's a 1 followed by 15 zeros. It is an absolutely enormous gap in our knowledge. So vast that physicists actually call it the Great Quantum Desert. Think about it. We've explored this tiny little coast on the quantum side, and we live our lives on the classical mainland way on the other side. But what happens in between? This desert is exactly where spontaneous collapse theories predict we're going to find the border, the point where superposition finally breaks down.
So the hunt is officially on. Physicists right now are building experiments designed to launch an expedition deep into this quantum desert. The whole goal is to keep pushing it, to take larger and larger objects, we're talking clusters of millions of atoms, and see if we can still get them to exist in two places at once. If we find a point where they just can't do it anymore, where superposition fails, we will have discovered a brand new law of physics. And if we don't, well, that means quantum mechanics is even weirder than we ever imagined.
And look, the stakes of this investigation are just immense. We could prove that the beautiful, elegant equations of quantum mechanics are actually just an approximation of something deeper. We could find out that randomness isn't just some weird feature of measurement, but a fundamental built-in property of the universe itself. This isn't just about tweaking a theory. This would be a complete shift in how we understand everything.
Which leaves us with this final, really profound question. Is the universe a story that's already finished, with every possible outcome just playing out in different worlds? Or is reality more like an unfinished book, with the next word being written, moment by a fundamental roll of the cosmic dice? The answer, it seems, is waiting for us out there, somewhere in the middle of that great quantum desert.